of language models. So I will start from the basic OPD, unprocessed distillation, and to some recent advancement of the OPD. Okay, so let's get started to know by knowing what is unprocessed distillations. So basically, we can see the three post-training recipe, and you can see that um, previously we have the supervised fine-tuning (SFT) or the reinforcement learnings. For supervised fine-tunings, the sampling is of course off policy. We have ground truth labels, but the reward signal is dense because we know actually for each for each tokens, it is a good because it's ground truth labels. And then for the reinforcement learning, we sample the models on generations, so the sampling is on policy, but the reward is normally sparse. For example, if we're using the GRPO, we're using the final accuracy to decide the reward for the whole generations. And then OPD can be seen as a mixture of the SFT and IO. It tries to combine the on-policy sampling with the dense reward signals. And we can start from the very first paper, like talking about the on-policy distillation, which is actually the GKD, we call it, from the ICLR 2024 paper, on-policy distillation of language models. So basically, for the GKD, for the original GKD, we have the X, which is the input prompt, Y is the student's output, PT is the teacher's probability or logics, or the models. P theta is the students, the model being trained. So basically, we will generate the student, generate the answer using the student. And then we will score each tokens using the students and using the teachers, which is basically the next token distributions. And then we will measure the gap, which compute a per token divergence D between these two distributions. Then we update our student parameter using the gap. So why from the student? Because we want on-policy training. One possible reason why we want on-policy training is if the student train on only teacher text, and inference would generate its own and his states is never stored in the training. And sampling Y from the student make the training state equal to inference state. So that's one possible reason why we want on-policy training. Then we look at the more details about the GKD. First is the loss functions. So basically, for one tokens, we will have the divergency between these two next token distributions. Then we over this distance at one tokens to the whole response. Then we just go through, iterate over all the student responses, which is the loss. Okay, and the only thing left is which divergency. So in the original paper, GKD used JSD, which is a combination of the forward KL and reverse KL. So for KL divergency, if you don't know, P and Q, if we change, for here, P and M, if we change the order, actually we will get the totally different results. And here they have M, which is the mixture of the P and Q. And if we beta is equals to 0, it's reduced to the KLPT given P theta, which is a forward, which means we need the P theta to become PT. And then if the P is equals to 1, we have the KL P theta given PT, which is we called reverse KL. So basically, um, uh, because the KL is not symmetric, these two actually has very different results. So we can see in here, the first one is forward KL, which actually called mass covering, which means if we use this KL as the loss function, the forward KL as the loss function, it will penalize the P theta whenever the teacher has mass. So the student must cover every student mode. Um, but it also has disadvantages. If the student lacks the capacity to express probability onto unlikely token, then uh, then if we're using the forward KL, the training will have some inference. We will not get a very good training result because the student lack of capacity to spare to simulate the teacher very well. And the second one is called reverse KL, which is mode seeking. So basically, the student will concentrate on the teacher's high problem modes. It never plays mass where the teacher has none. So it's sharper teacher-like samples preferred when the student is smaller than the teacher. Of course, this is um, the very beginning, the first method of the on-purpose distillation for language models. And as far as I know, it becomes much more popular in recent years because of one block from the thinking machine. Actually, they did not do much difference, but just do some minor changes. So first one, they do the change of the fixing the divergency. In the GKD, their divergency can classify by itself, but here they just using the reverse KL. And the second change is aggregated from one token, which means um, for here. If we want to calculate the scale, if we look at the formula, you can see we need to iterate all the vocabulary tokens, which means uh, like you need to calculate the distribution of the next token. But they change it to just to look at the sample token difference. So this is two biggest difference. Also, they also like um, do something else. For example, runs at a modern scale, and also opens a use case for personalized and continuous learning, which previous paper did not do. So, uh, like we in that broke, they actually also show that the KL loss gradient is also a policy gradient, which means we can uh, we can use the IO reinforcement learning perspective to look at the OPD. Here's a very simple derivative to show why their reverse KL like on this KL on just sample token can be transferred to a policy gradient. You can see here because of the KL we can write the KL in this form. Then with derivative, one token scale using the product rule, we can have this formula. And the second formula here is actually equals to 0. And then we only have this left. And actually, if we take this out, it actually becomes these things. Take the delta out, we can get these things. And then if we want to minimize it, we descend it. So basically, if we take the advantage equals to the probability from the teacher of sampling this token minus the probability of sampling this token, YT, from the student. This is an advantage we have. And then we're just using the policy gradient. We can get exactly the same update gradient. So that's why we could consider um, the OPD from the thinking machine block as an IO with the advantage is defined by this probability difference. Okay, so any questions for now? Okay, then we can go continue. And because in this sharing, I will share a lot of papers. I cannot show their results one paper by one paper, so I will only show some interesting results. But before to reason advance, let's firstly see the result from the thinking machine blocks. So here they firstly show the results on the reasoning. which they compare with the reinforcement learning, GRPO, and the off-policy distillations. And they claim that the on-policy distillation could beat the GRPO with only around 10% GPO hour because it only requires one more forward pass from the teacher, and and even achieve the better results. Another interesting is the resulting on personalization fine-tuning. So the task is to training on the internal documents plus the chat data. If we increase the fraction of the internal QA data set, of course, the internal QA evaluation results will increase. If we only use the internal QA data set to train the model, you can see it's 100% here, which is around the top. But the chat performance, which is a general instruction following, well, drops a lot, which means this is catastrophe forgetting problems. And one solution is to just using maybe 70% document and using 30% chat data. Could mitigate this problem. We increase both the internal QA and the IF evaluation, the general task. But if we also add the OPD here, we can get the best results, or maybe the best is balanced results, or you can see this as a Pareto optimal. I think they get the both. Yeah. Um. Okay. So that's everything uh for the for the for the normal on-point installations. So for now, anyone has any questions? If not, we will go digger deeper into the OPD. So
One thing,
yeah.
can you give the link to the slides?
Oh
Um,
yeah.
yeah.
Uh, sorry. Wait a second. Let me- Yeah, I sent it in the chat.
Okay, thanks.
Okay. Then today I will go deeper into OPD in this four four dimensions. Because if you look at back to the original OPD, this is a quite simple idea. And maybe I will say the two dimension is the most important. The first one is divergency, what divergency to use. And the second one is the teacher, which teacher to use. And the third part is integration with IL, which actually a little bit out of OPD because we use OPD to improve the IL instead. So it's basically IL method, not the OPD method. And then the final one is one OPD works and one it doesn't. Basically, I will show some papers try to unmask the OPD's performance. Okay, so first we get to the divergency, which is I think most the paper I see is in this topics. So I covered the most paper in the first topic. Um, so let's basically, though there's a different paper trying to solve them, trying to use the different diversity, but basically they want to solve these two problems, or sometimes someone want to solve it at one time, and some just want to solve one problems. So why the forward KL explode? This is because early in the training, the student gave almost no probability to many teacher preferred tokens. So the ratio diverges and update explodes. So this is basically means the teacher, as a student, does not have the capabilities to cover all the high probability tokens from the teacher. So so that's why forward KL uh will fail at sometimes. Um, And in the second part is why reverse KL collapse. It basically means it's penalized the place where the teacher is unlikely, yet it never penalize the teacher model the student that does not visit. The cheapest way to lower lower it is to pile all mass on one model. If you still remember this mode seeking. So the students grows overconfident and lose diversity. It will only try to learn one way to solve the problems. Okay, so this is the main problems these topics I mean this part of paper want to solve. So we can see the solutions one by one. And okay.
We have a
And if you
question from the chat.
okay, let me see. Would increasing the amount of mid-trained data while keeping the distribution setup unchanged improve coverage or overall performance?
I think is related to your previous topic.
Yes, I think that's you are talking about this one. Increase the amount of while keeping the distillation setup unchanged improve convergency or overall performance. Oh, I think that's a very general question. If we increase the amount of the training data, well, whatever training method we use, we should be able to increase the performance as long as the data is in good quality. Yeah. But I
But
think this
here, I think
is
you mentioned like if it's improving overall performance. Does that mean it's the left hand side or the right hand side performance? I don't know.
overall performance. It sounds like the general performance.
General performance, are you talking about the right hand side, the if
Yeah, the
block?
rise is, but I'm not sure if Yash, if you can explain. Um, yeah, we can like talk about this later, but I can uh go on. And defining overall performance seems like a combo of multiple task metrics.
So I think maybe he's asking if you here you add a distillation on the bottom line, right?
Uh-huh.
Then if you continue increase mid-trained, does that still improve?
Oh, I see. Uh, to be honest, I don't know.
Does the
Uh,
paper have anything about that?
I really don't think so. This broke. Uh,
Okay, this is just a blog.
yeah, this is a blog.
Okay.
Yeah. Um,
Okay. Yeah, if you don't know, that's all we know.
yeah. Um, oh yeah. So let's see back to our previous topics. So let's see how the first paper changed the targets to try to solve the problems. Um, so basically the f first paper proposed Vento. The logic of this change is they want to training on the tokens that both student and teacher have the probability. So it will remove the forward KL problems because right now the student can still already have some probability on the tokens that teachers want. So they how do they do this is they mix the teacher and the student in the logic space and uh, change it to a new KL uh, to uh, to a new like Q which is used in the KL loss they will calculate. So basically this Q is the exponential of the ZT plus beta ZS, which is the logics from student and teacher and it's exponential to this PT times PS beta, and then we use this Q to calculate the forward KL or reverse KL. So why this will work is because you try to make the forward stable. So it basically means if the PSV with the probability of the student to output this token is nearly zero, then because because the power be this low, so the whole item will goes to zero, which means the whole system will not learn in these situations. And then they also prove it converges to our sharper teachers, like as optimum. That's not just copy the teacher, but a sharper version of it, which make it more decisive. Uh, dis decisive. Okay, so I think this is why they do this change and why this change will work. And the second paper, they actually looking at the different tokens, which the paper is en entropy aware on post distillation of electron models. So a look back to the problems. Uh, why we need forward and reverse? Like if we only use the reverse, the problem is they might have different solution, but you only learn one solutions. But if the teacher only have one solution, of course we don't need to learn more solutions, and we cannot learn from it. So basically, uh, we need why reverse KL might fail. The reverse KL fail because the teacher maybe has multiple valid modes. And next question is, of course, if the teacher has this valid modes, we need to use the forward KL. So that's why they're using the entropy of the teacher's distribution to detect whether the teacher has two valid modes or just one valid mode. If we have one valid mode, we can just use the reverse KL. That's fine. But it has multiple valid modes. It has a higher entropy, and we need to learn using the forward KL. That's the total like logic and uh, the idea of this paper. That's why they call it entropy aware because they are using the entropy to detect. And then their loss function is very simple. They always have a reverse KL, and then based on the entropy, they will have if entropy is very high, higher than the tau, they will have the forward KL. So this is basically um, like they will change this tau to maybe 15 to 20% of tokens that are they think they are uncertain during the generations. So that's the basically every idea from this paper.
Can
And
I ask a question, TJ?
yeah,
Not for this paper, it's the previous one. So
yeah,
I was wondering if the yeah, this one. So if the student model and the teacher model, if they have different architecture, so their logic space maybe
yeah,
not align, right? How
yes.
can
So
you directly aid them?
actually, that's a problems in the second part. I will talk
Ah,
later.
okay.
Yeah,
Yeah, yeah.
yeah. Okay, so there's after this paper, actually there this EOPD, entropy aware on porous distillation. This paper try to say just using the entropy is not enough because they ignore the teachability, which means or the reachabilities, which means if the output distribution of the teacher and output distribution of the student, they are quite different even if you use the forward KL, it will not work because the model just cannot learn. It's just the distance is too far away. They cannot learn it. So they they have a new matrix they call the teachabilities, which actually using this subset, which means they will see measure how much the student mass lands on the student's on top K. They will, they will see on the on teachers' top K tokens and the student top K tokens, well, they overlap. If they are overlap, that means maybe they are easier to learn. And then they have the final like this how to say final matrix is this countability. This is reachability CT times with the forward KL loss to get whether this token is worth learning or not. We don't need to learn it. So this is basically from this paper, and they also um doing some experiment to show they are better. For example, compare with the entropy. If we only use entropy as a signal, whether we need to learn or not, the gain means the loss, the KL loss reductions. The gain is much higher, and the sparsity is much better, which means the teacher probability mass landing on students on top K. So basically, this paper want to solve if the teacher do have two valid modes, how could we learn? Is it possible we learn the both two valid modes, or we can just only learn like this, spread mass into the empty valley? Um, Basically, they don't want this to happen. So this is the idea of this paper. And actually, if we look at this token level operations, we could consider there are some similar methods that provide some very similar results and method using the IO perspective, considering the IO perspective. And it's so basically it means when we look at the IO, right? We look just quick recap, we have the advantage, which is the probability of the teacher minus the probability log probability from the students. And if this advantage is greater than zero, which means we have positive advantage, which means the teacher prefer this token more than the student. So this is called exploit. And we can just learn using the reverse KL because we want the output of this token to be further increased. So we can still use the reverse IL. But if in other words, if we have the advantage is lower or equal to the zero, which means the output the probability of the student is higher than the probability of a teacher, but it's highly likely this token leads to wrong answers because the teacher does not agree with you. And then maybe in this case, we need to learn more solution from the teachers, and we need to use the forward KL. So this is so basically this is their solution. Very simple. If we have positive advantage, okay, we don't change anything. If we have non-positive advantage, and then we just using the forward KL instead of the reverse KL. Like from idea, it's like dynamic entropy aware the OPD because if the student probability is greater than student probability, it means the entropy of teacher is low because it has a very high probability on this token. And then we keep the reverse KL. That's what we do in the dynamic in the entropy aware the OPD. And in the OPD, we have a gate, and here uh, we have a gate tau, and here they just using the gate as a probability, student probability. So I think the method is quite similar, and their key ideas when to use the forward, when to use the reverse. It's very similar. Okay, so right now we have seen like how do we change the divergence in the OPD. um, or when to use the reverse, when to use forward, this kind of things. But the next paper, which is also the final paper in this part, actually changed the pipeline a lot, though it's not changed the array pipeline. Basically, this paper's motivations and observations again, it's very similar from compared with the entropy aware OPD. You can see observation one is a few tokens have entropy several times the average. They think this might be a very important, but they also have another observation is those high entropy tokens cluster early in the trace. So this high entropy tokens will show earlier. Um, and then based on their observations, they have a new loss function instead of just a KL. They also have the KL loss function, which is this loss function direct. But they also have the loss function EM, which is entropy regularizations, and one loss function of the indirect. So let's see them one by one. The first one is the indirect distillations. Um, the student they were using the early generation because they found those high entropy tokens class early in the trace, so they only doing it in the early stage. They at the early position, the student puts forward its on top K candidate. They use the K equals to 10. Then the teacher only re-ranks them without getting the logic or probability. The the teacher reorder. I mean, I think they will just reorder this K, still reorder this K using the probability from the teacher, but not directly using the KL. The teacher will reorder those K by its own logics and return the order. And then they were using some like order loss functions to get to try to make the student's order equals to the teacher's order. So why indirect? I think it's because it's still the forward KL problems because we know if we forcing the four teacher distribution on every token overwhelms a small student. But if we're just ranking them, we're ranking the student on candidates, it's a much weaker feedback that maybe the student can learn more from it. And yes, and keep its reasoning on its own words and leave room to improvement. So I think that's why they have an indirect loss on the ranking. And of course, the second one is gated directed distillation. They use the GSD and with the entropy difference as the gated. Then they have entropy regularization. They try to reduce the top 10, not top 10, top 10% highest entropy tokens. So this is basically how they do. So basically, I think the most important is this indirect, or the most new, the most novel is the indirect, and why it will work. Is for these papers. Okay, so I think I finished my introduction to the first part, divergency. Is there any problems right now?
There's one thing I was wondering about.
Yeah.
When you're discussing the forward and reverse scale thing, right?
Uh-huh.
That if you try optimizing one,
Mm-hmm.
then it sort of becomes like difficult to optimize the other. It's kind of like the exploitation um, and exploration thing, right?
Mm-hmm.
So, did any of the papers use the JSD? Because I
Yes.
remember that being symmetric, right?
Yes. I think I like the very first paper uses the JSD.
Okay.
And and um and
But
of
what's
course
the problem with JSD and forward and reverse
because
then?
if you just use JSD, you don't solve the problems. You just leave the problem as it is. You use the
Okay.
reverse and forward, but together they both have the problems.
Oh, okay.
Yeah.
I see.
So just simple use the GSC does not solve the problems of
Oh,
what I'm doing. Okay.
okay.
Um. Also, like this paper, you can see they are using the GSD here. Yeah.
That's why it popped up in my mind. Why didn't the others used it? Yeah.
Yeah.
Okay.
Okay. Then we can move on to the second part, which is which teacher we want to use.
I
So,
I have a question here.
oh yeah.
So I think we want to do in last paper, we did some like gate to select some important tokens, right? So different weights on different tokens. But how do we select the tokens? It just depends on teacher, right?
Which paper? Because there are
So
so many papers.
I think it's let's go last one. Yeah, last one.
The last one. Oh, so the
Yeah,
last one,
yeah.
they do not select the tokens. Oh, you mean this one?
Yeah, I think there are different components. So right, so I think is this to do different tokens? So do different like component on different tokens?
No. So f for this component, of course, for the indirect, they only apply for the early position. Uh, but I mean, if they can apply, they will apply all. It's not they did not select which token they want to optimize. But some papers, for example, these papers, they actually uh or maybe this entropy aware token. Oh, nope. I think it's teachability. Yeah, these papers they will only optimize on the tokens that has a good teachability.
Okay, so it's a tokens is selected by the teachers in the paper. So
It's not selected by teacher, but
intro by
select.
intro pay, right?
Uh,
Intro.
no, this paper is selected by their own metrics, not just entropy.
Okay, okay,
And this paper, they will update I mean, they will update on all tokens, but only a few selected tokens will use the forward KL.
oh, okay,
And also for this paper, AOPD, um, they will also do the update on all the tokens, but positive one will get the reverse KL, and non-positive one will get the forward KL. Okay.
okay, gotcha. Thank you.
Okay. So let's go to the teacher part. So for the teacher part, I think Xiao's previous question is very is a core problems. One of the core problem is the uh cross family model, sorry, cross family model as a teacher. If we use the different tokenizers, we don't have the same logics, same probability space. And this paper shows two problems. The first one is if we look at the overlap of the tokenizer or vocabulary, you can see there you will lose around 50% to 70% informations. And if we don't have the same tokenizers, we will have the sequence mismatch. Like happy will be the difference, maybe from the different tokens. Of course, we cannot use the standard OPD. So in this paper, they talk about the previous paper, whether using the same family or they were using only the overlap part, only the overlap part to train the OPD. Of course, if we consider the cross family model, we use overlap part, it will lose a lot of information. So they have a new method. It's called the idea is using the overlap, which is this part, then union with A, which is the shared um, words between two tokenizers. So or they call it minimal aligned unites. So they will given the data set, they will firstly get this minimal aligned union A to get all the unions. So basically, for example, we have happy, maybe happy py, and then we will combine them to make it aligned. Okay, so we know happy is the minimum aligned unite. And then the next problem they want to solve is one for first one we have two tokens, and for the third one we have three tokens. We cannot directly compare with their logics or probabilities, so they do a rescoring. For the rescoring is they are using the log probability. You can see they was using the mean log probability of all the tokens in this minimal aligned unite. And then they were using this new score, which is the mean log probability, to redo the softmax things so they can they can calculate the KL on this new space, this new common space. So this is the idea of this paper. I hope this solves the problem from Xiao. And you can see it's actually very new. It's from the last month. Um,
Yes. So this one is from different family. What about in the same family, but they have different size? Like the teacher model is 72 billion and the student model only 8 billion or 4 billion. So I think the dimension will be different, right?
the dimension will not be different because they only compare with the final
The last
logits. Yeah, the last
oh,
year. It's not the layer by
okay, okay.
layer. Okay.
Okay, okay. Yeah, thank you.
Yeah. So as long as they have the same tokenizer, they can do it. And I think there's also one direction. I think they may still fair about this cross-modal things. So they have this new direction called unpolished self-distillations. So I read a lot of papers in this direction. At first place, I thought maybe it's worth doing one more sharing sessions to talk about unpolished self-distillations. But after I read them, I found their core ideas very similar to each other. I cannot see much difference. So I just put here and talking about its main idea. So for the self-distillation, we use the same model for both teacher and student. And of course, if we directly use them, we cannot let the student model directly become the teacher. So the solution is we add some information in the teacher prompt. For example, for these problems, for student prompt, we just provide the problems. For teacher prompt, we provide our reference solutions, and then saying after understanding use the reference solution to try to solve the problem using your own approach, bro. Um, you can see the only difference is how to generate the teacher prompt for the teacher. And to generate the teacher using the same model, I see a lot of paper did different things, but the key idea is just provide more information to teacher. They can allow for the ground truth answers. They can use the generated answer from a larger model, and they can use the hint to answer the questions, etc. And one more unique dimension might be they allow the teacher to update as well. For example, maybe every 5 steps of updating student, we will also change the teacher to the new trained student. So this is basically some ideas from different papers. And the problem is why using self-distillations? The first, of course, I think is mostly due to the memory and other constraints. And there are also some paper like talking about using model itself is better because the model knows the reasoning ability or of itself the best. So the problem of forward KL might not appear. If we look back to the like the teachability, you can see they are using the overlap between the student's top K and the teacher's top K. And then since the student and the teacher, they are the same model with different prompt, it's more likely they can learn better. This is the idea. Um, but uh, from all the papers, 4 to 5 papers I read about self-distillations, they do not compare to OPD or a large model with this information. I can only say they compare to the GRPO SFT and claim they are much better, but no directly comparison to OPD itself or a large model with the information. So I think there's some gaps here. By the way, I will also share some paper tries to the this comparison. Yeah, but it's not the master paper. Okay, so the third part is the integration with the IL, which is not the OPD. Before moving to the third part, maybe I can stop to ask if there are any questions right now. Okay. Then we go to the part three. It's integrated with IO. So basically, it's integrated with GPO for most paper I see, and they try to use the OPD as auxiliary loss to improve the GPO. And we can see one paper. Again, recap the IO perspective. We have the exploit, which the probability of teacher is greater than student. We have exploration is the student probability is larger than the teacher. We already see like how this exploit idea might use the for OPD itself. But this paper want to combine the OPD with the GRPU. In detail, they actually want to enhance the explorations. The key idea is when the generation is correct and the probability from teacher and student is quite different, we should try to encourage the exploration because the student discover a correct path that teacher do not see because the probability of teacher and student they are quite different. But this generation is correct. So they do a very simple check. It's to have a weight of the tokens. Um, basically they will try to use this weight. So with for a prompt X, they will firstly sample a group of K rollouts, which is standard for the GRPO, and then receive a verifiable reward, 0, 1, which is accuracy reward. Then we have a group standardized advantage, AK. Then we will have this weight is equal to the like the probability of student over the probability of teachers, then power with the power of the sign A, which means on positive advantage token, it's greater than 0, it's greater than 1. So it's actually increase the importance of such tokens if the student's probability is actually greater than the teacher's probability or is against the teacher predictions. So this is basically this paper's idea, how to use the OPD to improve the GRPO. And the second one is another paper. The second paper I want to talk is try to use OPD with agents. So I see the Hayang's comments about to introduce about these topics. But I only found there's few papers talk about OPD for agents specifically. Because for normal agent training, the model will see the special tokens like two core instead of real environment. We can still use any OPD checks for training agents because it just consider it as tokens. Just make sure the two core token is the same for the student and teacher, of course, and mask the output from twos. However, there's problems for distillations, and I will also talk about another possible problem in the later part. So from this paper, it says if we directly using OPD in some self-distillation problems or scenarios, it might reduce the tool usage. For example, if with the user ask question, what is an XX? The students will think, I have no idea, I have no information, I need to do a search. So that's why maybe the student will call the tool search. But if we look at the self-distillation, we will give the information. For example, if we give the information of the ground truth, x-axis are what, then teacher will see this information. Of course, it will directly answer x-axis are what. And when the teacher sees the trajectory from student, he will think it's unnecessary to call the two. So the information might make the teacher skip the tool usage. And the idea is not very hard. They use an external build stepwise credit reference. So basically, it will firstly ask the model, the student model, to generate the trajectories, and then using another external LLM to provide credit, like whether this trajectory is okay or not. Then provide this credit, only credit to the to the teachers, and then using that credit and the trajectory generated by the student as the teacher informations to the teacher, and then doing the same OPD. And actually, after I read the paper, I think maybe we could use the trajectory from a stronger external language model without answer information as the teacher information. It's a better solution because I don't know this pipeline, like using another external LM to provide the credits, a little bit like using the larger model as judge as the reward model. Um, Actually, I have also seen other papers that call itself the OPD paper, but actually they are using the teacher to provide the credit for each step, and then using that reward directly to train the model. I think it's more like the LMS judge as the reward model instead of OPD. Um, it's quite different from the OPD we have already seen. So I don't quite like it, but I'm not sure. I'm not sure actually. Yeah, and that's the part for the integration with IO part. So is any problem for now? Okay. Then let's go
I
to
have one small one.
uh-huh,
Can you go back a little?
uh-huh,
The first method you were
uh-huh.
showing.
Here.
Yeah. Um. Okay. They're showing the T here, but
Uh-huh.
how do they use the reward again?
They
Here.
will directly time this weight with the advantage to use it as the final advantage.
Okay. Okay.
Yeah.
I see. Okay. Thanks.
Yeah. Okay. Okay, so the final one is one OPD works. Oh, I see. I'll chat. I feel the pipeline figure of this paper GPT generated.
I'll just say you the pipeline you just shared.
Okay. You mean this paper?
Yeah.
Okay. Yeah. Yeah, I think that's another reason why I'm not quite like this paper. I think um it's not a very natural uh research paper. Okay, so let's move to the final part, which one OPD works and one it doesn't. So we will see some uh results finally. Okay, so let's see the first paper. It's called Unmasking on Process Distillation, where it helps, where it hurts, and why. So basically, they tries to unmask the OPD by showing whether their update gradient is good or not. So how to judge it? Um, they firstly build a very large generation tree. So for the same question, it will generate hundreds of the generations, and then just like each token or each yeah I think each token is one leaf, and then they will form a tree. No, sorry. Each token is on one node, sorry. And then they will form a generation tree of this hundred of generations. And then they will calculate, okay, if I goes to this token, but what is the probability of the um like the question the answer is correct. You can see we can get the probability of success. And then we could get an ideal to estimate an ideal gradient given these tokens, which is equals to this formula. So we have a ideal gradient. And then they will compare this ideal gradient with the distill gradient to see whether this distill gradient and ideal gradient they agree with each other. If they agree with each other, then the distill gradient is good. Otherwise, the distill gradient is not. Okay, so this is the idea how they do in the analysis. And we will show some most important insights or conclusion from this paper. The first one is incorrect rollouts show far higher gradient alignment than the correct ones across every setting on the matrix. So that's basically to say, uh, why we can learn from the OPD is because we learn from the incorrect rollout, not the correct rollout. I think that's rationalize why previous paper why they want to increase doing some analyze it's too far away I think. Yeah, but if you still remember some papers they will monitor the gradient or the divergency if the generation is correct, because if generation correct it cannot learn much uh using the original OPD. And the second one is uh, this table shows the mean gradient alignment by the teacher, and you the conclusion is that self-distribution wins for 0.6 billions, and then external teacher wins for 1.7 billions. So which means uh, a small student cannot absorb a much larger model reason styles, which we have already shown is the problems of the forward KL. And so they have the conclusion that if your model is very small, self-distillation might be good. But if your model is large enough, we could use a much stronger external teacher. And also here is they have this conclusion that there's no universal recipe. The best context flip with difficulties. So they have self-distillation, self-teachers with one correct future example and one wrong future examples. For the easy questions, the alignment of the 1C, 1W is actually the lowest. But for the hard questions, this setting will get the best results. And also, they do like to see whether we can use some features to predict their oracle like their oracle alignment here using the cosine similarities. Um, and this table shows the correlations, and you can see we sometimes we can it's around the best is around 0.04, but it's still positive. And sometimes it's 0.35. Yes, this is the best, I think. So sometimes you can, but in most cases, it's very hard to predict whether it's good or not using these single futures. And they say we only need to do the distillation on this good tokens. Good tokens means their cosine similarity is greater than 0. They only update using these tokens and says using only half the tokens they can beat the full GKD. Okay, so I think that's the conclusion from these papers, but actually it has a lot more experiments. If you have time or have interest in the on-policy distillation, you can take a look by yourself. And there's another paper doing a similar things, but they try to analyze it with different ways. So they are not analyzing the gradient, but they try to see the overlap ratios. If you still remember, that's the teacher's top K and the student top K, which maybe can decide the forward KL's performance. So they will care about this overlap ratios and overlap token advantage and entropy gap. So I can directly tell you the core idea or the core conclusion of this paper is OPD transfer the teacher's thinking patterns, not its benchmark skill. So a stronger teacher can fail when a weaker one succeed. So the first conclusion I want to show is the teacher must share the student's thinking pattern and must carry knowledge the student has not already seen. Which basically means they need to have high top K overlap, then this OPD or maybe the forward KL could be succeed. And generally, you need the new knowledge. Otherwise, you will not you even you have high high overlap. I think that's somehow trivial because if you are using the same model, you don't have any new knowledge, and even they have very high top K overlap. You cannot succeed. You cannot succeed because you're not bringing any new knowledge. And the second one is a stronger 7 billion teacher drives the student to the same level as its weak 1.5 per NIL checkpoint. So I think this figure shows the results. We have two different teacher. The first one is 7 billions. The second one is 1.5 billions. Their accuracy is quite different. I mean, the accuracy for the teacher is quite different, but their OPT results is very similar. So uh, that's why they are saying OPD overrides the student with teacher thinking patterns. A higher scoring teacher from the same family has no new knowledge, so it cannot help and can even regress the student. And um, again, they talk about when well OPD works. It means we need to overlap ratios, we need overlap token advantage approach to zero, and we want entropy gap narrows. And if we have these three signals, then OPD will not fail. Okay, and uh, the based on their observations, of course, we want the teacher and the student they have the high top K overlap, so OPE could succeed. Of course, we could do is we can raise the initial thinking pattern overlap, so the teacher signal becomes exploited. For example, we can do the output core start. We can do a SFT first from the data from the teacher's data. We can do a SFT first, and also we can use teacher aligned prompts. Try to make them aligned as much as possible. Okay, so the final one is if we look at the dance per token rewards works on moderate uh like the length of the generations and whether it will works for the longer generations. You can see the dance per token reward works on moderate length trace, but decays as the student perfect drift from the teacher. And also you can see the improvement from teacher continues will lost when we have a very long student perfect truncation length, which means if we generate a large context, maybe OPD will not work. So uh, I think one implication is OPD may not extend cleaning to long horizon train of thought or agentic settings. So that's another problems if OPD want to use in the agentic settings. It's about the long trajectories it will meet during the training. Okay, I think that's everything I want to share today. If you have any questions, I'm willing to help if I can.
Okay, any questions from the audience?
Well, I have a open question. I think most people will say OPD is a good post-training technique, but since we need a strong teacher here, does it mean for this, if we want to do some strong model, we will it's OPD only suitable for some smaller model or some new tasks. But if we want to go well, so for this OpenAI anthropotic, we want to develop very good SOTAS models. OPD will not work except unless we use a self-opposite distillation.
Um, so 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 firstly, I do not know. I do not know whether some SOTA model use the OPD or not. But I what I can get is the chance in the like in the Twitter or maybe in Xiaohongshu, etc. or other platform. I just feel like the OPD becomes uh, generally becomes more important positioning techniques for as people discuss it. But whether it's already used in any like SOTA model uh, or in the real industry, I'm not sure about it.
Okay, thank
I
you.
think from my side, our company already use the OBD to train some smaller model because they will use the large language model a lot of times in within one day. So if they want to save money, they need the OPD to train some smaller model to replace the large language model.
Yeah, okay, so from Xiao sounds, I think it basically right now it's only used in the small models.
Yes,
Um,
yes. Not for the
yeah,
SOTA model, I think.
yeah. I don't know for the small model whether they can be improved using the self-distillation. I
Yeah,
don't
that's my
know.
concern for the self-distillation, the OPSD, because they learn from itself.
Yeah.
If I think it can only improve the pass one accuracy. They cannot improve the pass K accuracy because the language model, the ability is already there. That's the upper bound the language model can learn, right?
Yes, as like from my opinion, uh, y- like for the reverse KL, we can only increase the past one, and and if we only
But
consider the self-distillation, we only provide one reference answer to the teacher. Then of course this teacher will only learn from these solutions. So basically, it will only learn one solution, which is has the same. I mean, it seems to me that it has the same disadvantage compared with the reverse KL only. Yeah.
mm,
I think the self-distillation, the knowledge in the self-distillation is from the privileged information in
Yeah.
the context of teacher model.
Yes. Yes. That's true.
But does that mean that the student model can never beat the student model? The student model can never beat the teacher model?
Um, I I do not think so.
No,
When
no, I think there is method, there is multiple method, and also there is a method called MADOPD. I will send there, and it used the multiple teacher models to
yes.
discuss, and then they sup make a superior performance than the student model.
the better performance you mean the pass one accuracy, right?
yeah.
Uh,
So my yeah, my question is like, does the student model have the chance to beat the teacher model? I can understand if you have multiple teacher model, then the one student model can maybe is ensemble. But if you just have one teacher model and does the student model can beat that teacher model? I heard someone mention like this is the upper bound of the teacher model is the upper bound of student model. Does that mean are you indicating that the student model can only achieve the performance of a teacher model?
Um, I believe I remember one paper I shared. They talk about this, but I somehow forget the over every context. But I think
I think in the OPSD paper, they, they show the result that the Cuban 3 8 billion model they use the OPSD.
oh yeah.
Yeah,
I remember it's this paper. They claim they are better than students, but this makes sense because it's
Yeah, it's using RL,
s-
right?
yeah, it's using the IL, not just OPD only.
Okay.
Um, oh. I because I remember some paper says they are better than this teacher. I need to check whether all that paper is coming from the IL part or just using
Okay.
OPG code. Yeah, I can
Okay.
provide the answer maybe next group meeting.
Okay.
Yeah. Um. Yes. Okay. Anything else?
I think, so for your, I think you said you can do some, no, uh, to try to train some models using OPD. So can we do it with closed source models or just open source? I think we need to assess the logics here.
Uh. For there is some method claim themselves as the black box OPD method, and actually their idea is quite like let me see this paper. The indirect this ideas this using some indirect ways to gather signals. I think I talked about some the PRM things. They're using the teachers to provide the reward for each step, and then using the reward to train the models. Uh, or using the rank, like ask the model, ask the another teacher to rank the trajectories or the reasoning trace, and then based on the rank, they train the models. But if we're talking about the if we define the OPD as this KL saying you must need the KL to train the model, yes, of course we need the logics from the teacher.
Okay, thank you.
But
Thank-
but
But the
but you have this self-distillation, right?
Yeah, for the self-distillation.
But it's for self-distillation, you do not need like your teacher is yourself, so you can have the logics for yourself. You don't
Yes,
need a
exactly. For the where is yeah for the self distillation you have the model yourself, so you definitely have the logics.
okay.
Actually, I have a question of the distributions. Yeah,
Yes. Mm-hmm.
yeah. I think distribution have embarrassing things because company don't directly admit that they distill from the other models, and people maybe will love this kind of company if they found that they distill others companies' models. So I'm wondering what kind of role does the distillation play in the industry or research, or how can people to better use the distillations?
I think one very legitimate action or usage of distillations is distill their own model from a large model to a smaller model. For example, like uh, I have a very large model to in my industry pipeline in some product pipeline, but I don't need I mean every time I use that large model it will cost me money, so I want to reduce the cost, so I want to distill the information from this large model to a smaller model. Then we can use like the distillation to get a good small model. I think that's also Xiao said, what Xiao said, right?
Okay,
yes.
I get you.
Yeah, and also this self-distillation thing, I don't know, but it may have the potential to even like increase the performance by yourself, by the large model itself, etc. So it's possible, though I don't know whether it works or not. So maybe it can also work for the SOTA model for the using the self-distillation. Then it's actually not a distillation, but actually a general post-training method.
I think I have saw some posts. So there are some reviews about the someone want to reproduce the OPSD paper,
Hmm.
and they said it's very hard to achieve this performance in the paper. So if someone want to do that, maybe we should be cautious. Yeah.
Yeah, okay. But I just feel there's a lot of paper in this domain self-distillation, but I think their idea is quite similar.
Yeah, and I also checked that for the DeepSeek, I think they use the multi-agent self distillation. They trained some of the domain expert and then use ample distillation to train one model here. DeepSeek for V4. Yeah.
Okay, so I see we have a lot of discussions. If you guys have any questions, just reach out to TJ on Slack. I think we are way out of time, but I really enjoyed the presentation and the sharing. It's really really helpful for me to understand this domain.
Oh, thank you.
Okay, I guess
Okay.
that's it for today.
Yeah.